Hello dear students, welcome to the Royal Palace PU College online classes. So in last class we have discussed about the oxidation action of what here concentrated HNO3 and dilute HNO3. So here we have the continued part, that is again here the oxidizing property of what here nitric acid HNO3, that is now concentrated HNO3 which oxidize what here iodine to iodide. So here the concentrated HNO3 that will oxidize what here iodine to iodic acid HiO3. So iodine, that is I2, that will oxidize in presence of what here HNO3, concentrated HNO3, that use what here iodic acid HiO3. So here I have written the I2 iodine, when they react with what here concentrated HNO3, there is a formation of iodic acid HiO3. So this is an iodic acid, and with liberation of what here water molecule and nitrogen dioxide. So this is an oxidizing action of what here iodine to iodic acid I2, that will undergo oxidation in presence of concentrated HNO3, that use what here iodic acid HiO3. Okay. So the next one, concentrated HNO3 also oxidize what here carbon, that will oxidize to carbon dioxide. Now here also the carbon which undergo oxidation in presence of concentrated HNO3 and that carbon which oxidize what here carbon dioxide. See here in both the cases the concentrated HNO3 which is an which is an oxidizing agent which oxidize what here carbon to carbon dioxide, and the first one reaction, that is iodine to iodic acid. Now iodine which will oxidize to iodic acid and carbon which oxidize to carbon dioxide. Here I have written the carbon when they react with what here HNO3, the carbon which undergo oxidation and that oxidize to what here carbon dioxide, and with elimination of what here with respect to water molecule and nitrogen dioxide. So this is another one oxidizing reaction. So the next one concept, that is brown ring test. The brown ring test, which is a test used to detect the nitrate ion NO3 minus ion. Okay. So here the brown ring which is formed, the brown ring formation is due to the formation of what here that is nitrosoferrous sulfate. So FeH2O 5 times NoSO4. So this is a complex, that is nitrosoferrous sulfate. The color, the brown ring is due to the formation of this complex, that is nitrosoferrous sulfate FeH2O 5 times NoSO4. Due to this formation of complex, and we are going to observe that what here a brown ring, that formation of brown ring confirm that there is a presence of what here nitrate ion NO3 minus ion. Here what happen, Fe plus 2 that reduce what here Fe plus 2 ions. So Fe plus 2, that is from the ferrous sulfate solution. Okay. So this Fe plus 2 that will reduce what here nitrate to NO3 to, that is nitric oxide NO oxide here NO. So this is the Fe plus 2 which reduce what here NO3 minus 1 to NO. So this is an test which is used to detect what here nitrate ion. So here the procedure for this brown ring test. So this concept, the brown ring test, so what happen, the salt solution which containing what here nitrate ion first you have to take. Okay. The salt containing nitrate ion you have to take what here in test tube. So to this test tube you have to add what here concentrated H2SO4. Okay. So here this test tube which is cooled under what here tap water. So after addition of this concentrated H2SO4, so this test tube there is a liberation of large amount of heat can be takes place. That means the test tube that will become so here very hot. So that test tube you have to cool under tap water. So after cooling you have to add freshly prepared FeSO4 solution, ferrous sulfate solution. So after addition of freshly prepared ferrous sulfate solution along the sides of the side wall of the test tube, slowly you have to add. So after addition there is a brown ring which is formed between the junction of the two liquid. So that confirms what here? Presence of what here? NO3 minus, nitrate ion. So that brown ring which is formed between the junctions of two liquid, so that confirms what here? The salt containing what here? Nitrate ion. So this is the procedure of what here? Brown ring test. Brown ring test which is used to detect what here? Nitrate ion which are present in the given salt. So by adding what here? Concentrated H2SO4, sulfuric acid and freshly prepared FeSO4 along the sides of the test tube. So there is a formation of brown ring. So that formation of this brown ring is due to formation of that complex, that is nitrosoferrous sulfate, FeS2O5 NOSO4. So now the uses of that is nitric acid. So first one uses used in the fertilizers like ammonium nitrate, manufacture of fertilizers like ammonium nitrate. So in the manufacture of fertilizers the nitric acid is used. So next one in the preparation of what here? Some explosive. So these are the two uses of what here? Nitric acid. So here next one concept, that is phosphorus halides. So phosphorus they form what here? When they react with halogen they form the halides. So mainly two types. So that is PX3 type and PX5 types. So phosphorus trihalide and phosphorus pentahalide. So these are the two forms of what here? Halides. When phosphorus react with halogen, and there is a formation of two types of phosphorus halides. The one is phosphorus trihalide, that is PX3, and phosphorus pentahalide, that is PX5. So here the first one, preparation of phosphorus trihalide. So the phosphorus trihalide which is prepared by the reaction of what here? White phosphorus. This is an allotropic form of phosphorus. Okay. So allotropes, phosphorus having allotropic forms, that is red phosphorus, black phosphorus, white phosphorus. So here I have taken the white phosphorus when they react with what here? Dry chlorine. Dry chlorine, there is a formation of what here? Phosphorus trihalide. So that is P4. This is a white phosphorus. When they react with dry chlorine, so there is a formation of phosphorus trichloride. So this is the structure of phosphorus trichloride. So having one lone pair of electrons on the top of the phosphorus and remaining 3 chlorine which are bonded to the what here? Phosphorus. Okay. So the structure which is similar to what here? Ammonia. So in case of ammonia also, on the top of nitrogen we are going to observe what here? Lone pair of electrons. Again there are 3 bond pairs are there, the nitrogen which are bonded to the 3 hydrogen atoms. So same thing here, in case of phosphorus trichloride also, we have one lone pair of electrons on the top of the nitrogen phosphorus atom, and remaining 3 bond pairs are there. So 3 chlorine atoms which are bonded to the phosphorus atom. So for that reason the structure is what here? Pyramidal in shape. Pyramidal shape. Pyramidal shape. So this is the structure of what here? Phosphorus trichloride. Trichloride, which is prepared by the reaction with what here? White phosphorus and dry chlorine. The next one, that is phosphorus pentachloride. So here the white phosphorus react with what here? Again dry chlorine atom, dry chlorine. So that gives what here? Phosphorus pentachloride. So phosphorus P4, that is white phosphorus react with dry chlorine, that gives what here? Phosphorus pentachloride. The structure is triagonal bipyramidal structure. This one, triagonal bipyramidal structure, having 3 equal bond length, So these 3 bonds are called what here? Equatorial bond, and these bonds are short. And again the remaining 2 bonds, that is these 2 bonds are called what here? Axial bonds, having bond length somewhat larger compared to this equatorial bonds. Hence here in case of phosphorus pentachloride the structure is TBP, triagonal bipyramidal structure, having 3 equatorial bonds, the bond length is shorter, and 2 axial bonds, the bond length is somewhat longer due to the repulsion. So now let us, I will move for the concept, that is oxo acids of phosphorus. So this is important for your examination, structure of, oxo acids of phosphorus. So here they have given the first one oxo acid name, that is hypophosphorus acid. So here you have to remember only the important thing is what here, the formula of the compound, hypophosphorus acid. So hypophosphorus acid, the formula is S3PO2. The nitrogen, that means phosphorus, you have to remember that the phosphorus having what here, 5 bonds usually. The phosphorus which is bonded to the 5 bonds. Now here we have this structure S3PO2. The name of this one is hypophosphorus acid. So first you have to write the phosphorus atom at the center. And you remember that one, the phosphorus which will bond, which will maximum valency, that is 5. Now what happened, here one oxygen you have to write by using double bond. So remaining 3 bonds which you have to write first. And after writing one oxygen, remaining one oxygen is there, you can write anywhere to this bond. Okay, I will write here one oxygen atoms. So totally P1 is there, I have written at the center, and the oxygen 2 are there. I have written already phosphorus oxygen 1 double bond, first you have to write, that is compulsory. Remaining one oxygen I have written here, you can write anywhere, this either here, okay. And totally here 3 hydrogen atoms are there, you can write H, H, H. Okay, so this is the structure of what here, hypophosphorus acid. Here also same thing. Okay, first you have to write phosphorus oxygen double bond, that is compulsory. So after that remaining oxygen you can write remaining 3 bonds anywhere, either here, either here, either here. After that you can write the hydrogen atoms. So this is an hypophosphorus acid. So this is first one structure. Now here the second one oxo acids, that is phosphorus, that is orthophosphorus acid. The formula you have to remember, S3PO3. So here you have to write first phosphorus, and then there is a compulsory one double bond oxygen, and remaining here we have 3 bonds, and totally here we have 3 oxygen atoms, already 1 oxygen atoms we have written. So remaining 2 oxygen you have to write. So after this we have 3 hydrogen atoms, you can write 1 H, H, H. So this is the structure of what here, orthophosphorus acid. Orthophosphorus acid, similar structure this one. So again the same concept here, S3PO4, this is an orthophosphoric acid. Orthophosphoric acid. First you have to write center phosphorus, 1 double bond O, that is compulsorily. Remaining 3 oxygen atoms are there, you can write it separately, and hydrogen you have to write separately. So this is a structure of what here, orthophosphoric acid. And now here the hypophosphorus acid, this is an having basicity is 1, because the phosphorus OH bond is only 1. So for this reason the basicity of this hypophosphorus acid is 1, because it having only POH bond, that is only 1 POH bond. For that reason the basicity of this hypophosphorus acid is 1, and it is an reducing agent due to presence of what here, pH bond. It is an reducing agent because of presence of what here, pH bond, and due to presence of 1 POH bond, and it is an POH bond. So the basicity is 1 for this hypophosphorus acid. Here the basicity is 2 due to presence of what here, 2 POH bond in case of orthophosphorus acid. Due to presence of 2 POH bond, and the basicity is 2, and it is an reducing agent because of presence of 1 pH bond. Okay. Similarly here also same thing, the basicity is 3 because presence of POH 3 bonds. There are 3 POH bond, hence the basicity of this orthophosphoric acid is 3, and due to absence of pH bond, it is not an reducing agent. It is not an reducing agent. Okay, with the structure of oxo acids of phosphorus, the group number 15 elements concept completed. Now the continue next group number 16 elements. Now here the group number 16 elements consisting oxygen, sulfur, and selenium, tellurium, and polonium. So the group number 16 elements consisting what here, oxygen, sulfur, selenium, tellurium and polonium. Now the occurrence, the oxygen is more abundant element on earth crust around 46.6%. In dry air, so the volume of air, that is dry air, contains 20.946% oxygen by volume. So this is an occurrence of what here, oxygen atoms. And selenium and tellurium found in sulfide ores. So the next one concept, that is general properties. So now the first one, that is general properties, that is electronic configuration. So general electronic configuration, the outer most general electronic configuration, that is ns2 np4. Okay, so ns2 np4, this is a general most valence cell electronic configuration of group number 16 elements. Okay, so here in group number, that is 15 elements, in previous group elements, the electronic configuration, valence cell electronic configuration, that is ns2 np3. Here the p orbital exactly half filled. So due to that reason, the group number 15 elements are somewhat stable, because already we know the concept, exactly half filled and completely filled orbitals are more stable. Now here in this case what happened, the outermost valence cell electron configuration ns2 np4, because this is a group number 16 elements. Now the atomic and ionic radii, so this is a second concept, that is atomic and ionic radii, atomic and ionic radii. Now here what happened, so the atomic and ionic radii, already we know that down the group, the size of the atom will be increases, the size of the atom will be increases due to addition of what here, extra subcell. Due to addition of subcell, the down the group, the size of the atom will be increases, size of the atom will be increases. So here from oxygen to polonium, the size of the size of the atom, atomic radii and ionic radii increases due to addition of what here, extra cells, subcells. So for that reason, the down the group, the size of the atom will be increases. So this is a concept regarding what here, atomic and ionic radii. So from down the group, the size of the atom, atomic radii, ionic radii increases due to addition of what here, extra subcell. Now the third one concept, that is ionization enthalpy or ionization energy. So we know that definition, ionization enthalpy or ionization energy, it is defined as amount of energy required to remove the outermost electron from an isolated gaseous atom. So whatever the energy required to remove the valence electron, so that energy, required energy, is called what here, ionization energy. See here, down the group, ionization energy will be decreases. Down the group, ionization energy will be decreases, because so down the group what happened, the distance between the outermost electrons and the center of the nucleus, what happened, decreases, because the size of the atom down the group increases due to addition of extra subcell. So for that reason what happened, the distance between the nucleus and outermost electron increases. That means what here, the force of attraction between nucleus and outermost electron decreases. So that due to decrease in this force between nucleus and outermost electron, the electron which are easily removed from the larger atom, larger size atom, because there is a less attraction between nucleus and electron. For that reason, the ionization energy decreases down the group. Okay, as increase in the size of the atom, the ionization enthalpy, ionization energy, the amount of energy required to remove the electron, that will be decreases as increase in the size. Whereas as decrease in the size, so what happened, the force of attraction between electron and nucleus will be increases. So hence to remove this electron we require what here, more energy. So hence along the period the size will be decreases, you know that one, the size of the atom along the period decreases. So for that reason along the period ionization energy will be increases. Down the group the size of the atom increases, the ionization enthalpy will be degrees. So this is a concept regarding what here general properties, that is electronic configuration and atomic and ionic radii, and third one ionization enthalpy. So in next class we will study next general properties of this group number 16 element. Now I will stop here. So thank you for watching my video. Thank you.